Standing just 60 feet 6 inches away from home plate, a pitcher relies on the complex laws of physics to guide his next pitch in for a strike. Whether he's throwing for power or finesse, his main objective is to transmit energy from the ball by generating momentum with his body. To do this, he's created a dance-like routine called a wind-up. This motion requires a biomechanics motion called sequential summation of movement. In other words, largest body masses move first, followed by progressively smaller ones. The pitcher starts the process by shifting his weight through his legs and hips and thrusting his body forward. Over 3 horsepower is generated through his body, which moves through his shoulder, arms, wrists, and finally, fingers.
Yeah.
Releasing the pitch, he transfers roughly 1.5 horsepower to the ball. But as soon as the ball is released, air friction starts slowing it down at a rate of about 1 mile per hour every 7 feet. This means a fastball clocked at around 100 miles per hour as it crosses home plate actually, at its release point, has a muzzle velocity of 108 miles per hour.
Yeah.
An overpowering fastball is what every pitcher strives for. The law of physics tells us the force of the pitch is directly affected by 2 factors. The first factor is the power generated in the legs as the pitcher drives towards the plate, and the second factor is the arm trajectory. The advantage here goes to a taller pitcher, just as a twirling rock on a long string has more angular momentum than the same rock on a short string. A tall pitcher can release the ball with less force and still achieve the same velocity as a short pitcher. But no matter how fun it is to see a pitcher hurl the ball at 100 miles per hour, a true fan only cares about the end result. A baseball may seem simple, but a host of complex physical forces take charge of the minuscule 3-inch ball when play begins. Size and weight have as much to do with the baseball's flight pattern and velocity as the hand throwing it or the bat hitting it. And we know this because of the law of physics. Whether it's thrown or hit, the ball and plate is governed by 3 major forces. Let's count them. The first is gravity, which exerts a continuous downward force. You know what they say, what goes up must come down. The second is drag force. This is the air friction encountered by a ball in flight. Air acts like a fluid, which impedes the ball's path. As soon as the pitch is thrown, air works against the ball to slow it down. Now these stitches aren't here for decoration. They break up the airflow, which actually reduces drag and enables the ball to fly further than if it was smooth all the way around. The third force determines the ball's trajectory. Magnus force describes an imbalance of airflow past the spinning ball. When a ball spins, air is forced to move faster in the direction of the spin. The faster flow results in lower air density and causes the ball to move in that direction. It sounds complicated, but all you need to know is that the ball flight path is determined by its rotation. Scientists have been so intrigued by the effects that these forces have on the ball. They've used wind tunnels, strobe photography, and other sophisticated technology to study them. The biggest question they wanted to answer was whether a curveball actually curves, or whether it's just a mirage. After years of debate and published reports from both sides, the latest tests conclude that, yes, the ball does curve. As much as 18 inches for a skilled pitcher, which is almost imperceptible to the hoi polloi in the stands. And that's what makes the curveball so hard to hit. Now scientists need to figure out how to hit the darn thing.